Hello all, this is Ranjit from H1 Hacks. Great to be a part of the awesome community where we are growing day by day. Feel free to ask your questions in the comment box below. Sharing is caring. So why not share our Facebook page and YouTube channel and Twitter account and support us so that we can come up with more and more exciting sessions. If you're willing to take a talk or training, please get in touch with us through email as given in the slide. Hope you guys enjoyed our previous Astra series. We'll be coming again with more and more exciting sessions on Astra series. In Astra series, we'll be introducing new tools and conducting reviews on existing tools used for penetration testing. So stay alert. So today's topic is on IoT. As most of you know that IoT applications collect more and more previously unexposed, often confidential data and allow access to various control functions over the internet. So security becomes a major challenge. The main problem is that because of the idea of networking applications and other objects is relatively new, security has not always been considered in product design. And IoT products are often sold with old and unpatched embedded operating systems and software. Well, as you all know, today's speaker is Jiggasu, who is a great friend of mine and who is well known in the security community and conferences. So he is here. Hi Jiggasu, how are you? Very delighted to have you here.
I'm good, Ranjit, and thanks for having me here. Well, H1 Hacks is a great growing online community which helps people to stay updated in InfoSec trends.
Well then, you can start with your session.
Thank you, Ranjit, once again. Hello, everyone. Welcome to the session, The Breakers of IoT. In this session, we will be talking about the hardware inside of IoT security. Before starting, there is a disclaimer that the opinion and the thoughts presented during the course of this presentation are my own and do not reflect the views or positions of my employer. To start with the introduction about me, I'm a security enthusiast working with Royal Philips as technical specialist in product security. I am active in security communities like Null, Sysinfo, and ISRA. I have done certification in security, and I'm very much interested into everything which comes about the security, especially into IoT and large scale infrastructure and SCADA security. Agenda for today's session would be the overview of our IoT and embedded devices. Then we'll be talking about the hardware and internals of IoT boards, embedded devices. Then we'll see how do we read reverse engineering of those devices, and then the outcome of the reverse engineering, either it is binary or firmware, how do we do binary analysis and reverse engineering of that binary. To start with the content, what do you understand by IoT? So IoT is nothing but a system which can talk to the other system either in intranet or over the internet. So if we see the example in current days, few of the people have the Fitbit or any other kind of fitness band with them to track the fitness activity of day-to-day basis. These kind of devices can be synchronized with your mobile application, which and calculates the day-to-day data and analyze that data and gives you a figure of your day-to-day activity and your fitness schedule. So this is the one example which we have seen nowadays near to us. But apart from that, if you see in homes, there are devices which are connected to your mobile application. You can control them and you can collect the data from those devices, and the data goes back to the cloud where it can be analyzed or it can be controlled to do analysis of that data. So if it is a fitness band or a washing machine which is connected to mobile application or a air purifier which can control over internet or any device which is there in your home and controlled over a network comes under the category of IoT. So if I talk about a home, we had TV, music system, lighting systems, cameras, washing machine and other smart locks in our home nowadays, which has connectivity through router to your network and can be controlled with your phone via either a Wi-Fi, a Bluetooth, NFC, or Zigbee kind of technologies. And there are many other ways or protocols. But the thing which is common in all the devices are the connectivity and the control over a network. Since the devices can be controlled over a network and are connected to your mobile application or to your social profile or financial profile or a healthcare profile, these devices might contain those data into their local storage or into the firmware itself, or these kind of personal identifiable information can be transmitted between the cloud and the device. There could be a possibility of transmitting sensitive information like your financial information or your PII or your healthcare information, which is either transmitting over a network or has been stored into the device itself, and it can be stolen from the device or into the transit. And that's what we will be looking for today. What is the sensitive information we can steal from these kind of devices? And how do we find out this information from the device? With a hardware reverse engineering. So here we have a figure of a living room of a home where devices are connected with each other. We can see television, music systems, coffee machine, temperature sensors, lighting systems has a connectivity over the network. And just imagine, since it is in the network, it has the same kind of attack surfaces which a network has. So it can also be hacked or attacked by any external attacker, and your connectivity to your even your coffee machine or your lighting system can be broken by attacking through the network. And secondly, as we have already discussed, that the vulnerability which exists on these systems can lead to leak your sensitive information out of it. So as of now, we have already understood a bit of IoT security. Why do we need it? Since everything is getting connected to the new smart devices, IoT devices are being added to your home, your personal network every day, every month, and even every span of time wherever you go. Not even in your home, but in enterprise section also. If you see, concepts are coming for IoT like bring your own device and bring your own solution to work with. And each device is built by some different standards, different technologies, and combination of each other. So there's a need of doing a security research on these kind of components apart from a traditional security pen test approach. So just to see how these kind of vulnerability are being attacked and how IoT devices can be vulnerable to this kind of attack. So we have two examples here. One is the disclosure by Billy Rios, where he has mentioned about a vulnerability that is hard-coded password into the firmware of a device. So what can go wrong if you have the hard-coded password into your firmware? Since this particular firmware is being used in the similar kind of devices and the family of the devices. If you do reverse engineering of one device firmware and you get the password of one device, that means you got the password of each and every device of this kind and manufactured by the same company. Secondly, we have seen a recent attack that was a distributed denial of service attack over the internet on all of the IoT devices. In this particular attack, the attacker has done a DOS attack on millions of devices by making them a bot of the botnet network. It was considered to be biggest DDoS attack on IoT devices ever. And the vulnerability on these IoT devices was led by a misconfiguration on all of the IoT devices. So here we have an example of IoT attack surfaces. So basically, there would be some devices, there would be a mobile application, there would be a IoT gateway, and on the back end, there would be a cloud which is collecting the data of IoT devices. So devices might use any kind of SDR to connect to other device, either it is mobile application or any other device which is connecting to. Then it can send the data to the cloud. Same as well as the mobile application can get the data from the device and send it to the cloud. So as we analyzed what could be the possible entry points into the IoT devices. To start with, reconnaissance, there is Google, which answers everything about anything. So if you wanted to know about any device, you can just ask Google about it. Then there's Shodan and Senses, which are specialized IoT search engines. These search engines gives you details about any device which is IoT or any connected device has a IP address and running over internet. These search engines can tell you what the service is running on the device, which are the ports which are open in the device, and the version of service running for the particular port. So you can actually access the device over internet through its services. Then comes about the GitHub. Many of these IoT devices use firmware or libraries which are built or available on GitHub. And since GitHub is an open source library and platform, you can find out, open firmware. custom library, and other information need to be built on a IoT device. But the problem here is, since the public information which is available on the GitHub and used in IoT devices but not customized, some of the vendor might use the current available version and the files or the library from the GitHub, but they do not customize or change it. So whatever is available on the GitHub, they are available on the board of IoT device. So you can actually find out the actual firmware or the files or the library running on the device on the GitHub. By finding these details, you can actually do a reverse engineer there itself and find out the sensitive information from these kind of component without even opening a hardware or getting a firmware out of a device itself. Then comes about the communication channels. There could be multiple software defined radio communication protocols there, either Wi-Fi, Bluetooth, NX, NFC, or Zigbee, or RFID sometimes. All these communication channel has their own exploit available over the internet, or we can customize and make their exploit according to the configuration of the component. Then comes about the communication protocol. COIP, MQTT are the most common communication protocol on IoT devices, which does not have so much memory or calculation power. Then it is possible to have a web server running on the device, or there is also a possibility to have a custom protocol over a IoT device, which we need to analyze and do a reverse engineering of that particular protocol and find out the data out of it. Then it comes about the application interface of the device. It can either be a user interface on the device itself or a remote login to this particular device. Next is hardware interfaces, which we are focusing on in this particular session. So we can find out the communication protocol in hardware like JTAG, UART, SWD, and etc. These protocols have their own way to transit data between the components like E2P-ROM, flash ROM, and microcontroller unit or microprocessors. Apart from the communication channel of hardware, there are low density storage memories available into the devices, that is either SD card or E2P-ROM as we mentioned, and also flash ROM, and sometimes the microcontroller units memory area. Also very important thing which we look for in IoT devices are the firmware of the device. This firmware can either be available on the low density memories like E2P-ROM, flash ROM, or it can be found in microcontroller unit or microprocessor unit itself. The firmware contains most significant values and information for the device. So we will be considering the hardware interfaces part of IoT devices in this session. So how to exploit any hardware's board and its embedded part. As in any other pen test technique, reconnaissance is also one of the first technique we approach in IoT exploitation. To find out open information available for that particular device, we can search it on search engines like Google. Then we can also do a search on IoT search engines where we can find out whether this kind of devices are available over the internet or not, and which kind of services running on that particular devices if it is available on the internet. Also, the public information like FCC ID, which is compliance for the electronics devices meant to sell in US, should be there on the device. It by having the FCC ID of any device, we can find out the public information available for that particular device. We need to search it and find out what are the components available on that device without opening it. We can find out the data sheet. We can find out the details of the chips and components are being used and any other test or data available on the internet about that device. Next comes about the hardware teardown, where we open a device by bypassing the hardware protection, or we can say we break the device to open the components of the device chipset and board. Once we open the device board, we need to look for the chipsets, components, buses, and interface on the board of the device. Then we need to connect through those buses and interfaces and components, and we need to get the data out of those components. Once we need to Once we get the data out of the device, we need to figure out what are the information which is very useful for us or can be a backdoor for us or can be sensitive enough for a device to expose. So as a first category in reconnaissance is Google. Google can tell us about any device which is available in the market. You can do search for its data sheets, its design documents, service manuals, user manuals, and from those documents you can find out the default user IDs, credentials, passwords. You can find out the services running on particular device. Like sometimes in any of the device there could be a web server running, or you can find out how to access the device just by doing a Google search of that. And next, as I told, FCC ID is very important thing in the case of the devices which are being sold in US, because if you search about FCC ID of any device, you can find out the internal details, internal photographs, data sheets, its test reports sometime over the internet publicly available. Next comes about the Shodan search engine, which is a search engine for IoT device, as we discussed. Here you can see if we search about a device, let's say Linksys router, you can find out list of Linksys routers connected to internet over the world and categorized by their services running. So as you can see in the example, there's a Linksys router and it tells about the location of this router is China. It says that there's a HTTP server running on that. And since you are able to see about the services running on particular device over the internet, you can exploit that and find out the related exploit of that particular service and exploit that. Next comes about the GitHub. As we have already discussed that few of the IoT devices use components, libraries, firmware available in open source repositories like GitHub, which are not at all customized but used by default. So, what we can do is find out that particular firmware from the GitHub itself. We can find out the mechanism of security has been kept in this particular firmware. We can find out the sensitive credential and information which are kept in this particular firmware itself, and any other information which is beneficial to attack a device. Next part comes as hardware teardown. To do breaking of the device, we need few of the instrument which are common in electronic like screwdrivers, which are very essentials. Sometimes we also need heat guns if it is sticked by glue guns or any other thing. Sometimes if the device is very teeny and small to open, we also need microscope. So this is just a general list to open a device. We might need some other cutters or kind of other devices. According to the device, we might need to judge it and need to open the device. Here is an example. When we open a device, the chipset looks like this. So what we can see here is some registers, some chips, some data lines, some interfaces, which we can figure out how these components connect to each other and communicates, and see how we can extract the information out of it. Next is after opening the device, what do we need to do? We need to analyze the circuit of any board. We need to identify the components available on the board. We need to identify the test points which are connecting from one component to the other components. Then we need to trace these kind of information. So as an example, if you see a device chip and you are not able to identify which manufacturer's chip it is, there's LNX website where you can match the logo of particular chip and find out the manufacturer of particular chip itself. Then when you identify the chips, next step is to find out the data sheet of particular chip, because there you find out what are the pins which this particular chip is using to communicate the data or bits to other device or other component. Once you identify the pins, you might need multimeters to judge the continuity or the actual pinouts on the board. Once you know about the data sheet and the pinouts, you might also like to identify what are the hardware communication protocol it is using. Like in case of microcontroller units, either it is JTAG or UART or any other things like I2C or SPI also. And these kind of components are being used in communicating the data between microcontroller unit and memories like E2P ROM or flash ROMs. So here is a list of components and protocol which you need to observe when you open the device. As most common hardware protocols you can analyze on a embedded board are UART or a JTAG or SWD or SPI or I2C. We will be talking about few of them in next slides, that how to interact with these protocol and how to get data out of it. Next comes about the embedded components available on the board of embedded device, which could be either flash memory or E2P ROM kind of low density memory. And then there would be either a microcontroller unit or a microprocessor unit sometime. Additionally, you could also find out either a USB or a Ethernet or a serial port on the board of embedded device, which again has separate ways to sniff data from and to exploit. So let us talk about the first hardware communication protocol, that is UART. UART is very common in most of the devices because it is the easiest interaction between two components of the board. It is basically a serial connection between two components, which is a asynchronous communication where you do not need any component to be a master or to be a slave. There are two separate lines for each component to send and receive data, that is called TX and RX. And since there are two separate lines to transmit the data for each component, you do not also need a clock signal to acknowledge whether the data is coming or going. And since it is a direct debug connection between two components, you can tap in between this connection and you can ac- see and sniff the data which is going between this communication. Since UART is also being used for debugging purpose, you can actually dig into this interface and see what data is going. Also, you can run some system level privilege command on UART shell and get most of the data out of this UART. So to identify a UART connection, you need to identify four pins on the board of embedded device. First is TX, that is transfer, then RX, which is receiver, then VCC, which is voltage, then ground. As an example of this reference board which is given on this figure, you can see that on the right corner there are four adjacent pins are available. So this is the first indication that it could be a UART because there are four adjacent pins together. Next indication for UART is that the first pin would be surrounded by a square print and other three pins would be surrounded by circle print. Once you have identified these four pins, you need to actually identify which one is TX, which one is RX, and VCC and ground. Although to communicate UART communication, you need to have only three pins, which is TX, RX, and ground. Fourth pin, which is VCC, is just to identify on which voltage this board is running. So to identify these pins, you need a multimeter to do a connectivity check and a voltage check to identify which one is TX or RX or VCC or ground. And once you identify all four pins, you need an additional tool called USB TTL or serial connector. This connector you can plug in your laptop and the other end you need to connect on the pins of the board. Additionally, you also need to understand what is the baud rate of this UART connection to get most significant data out of the UART connection. If the baud rate is not correct, you might need to read the data sheet or the user manual or service manual of the device to understand about the baud. Otherwise, you will not get proper data from UART connection. To access UART, You need to plug USB TTL serial connector in your laptop's USB port and the other end of the which is connect. You need to connect RX of the connector to the TX of the device and TX of the connector to the RX of the device. Then you need to match both of the ground of connector and the device. Once this connection is ready and device is in operational mode, you can see the data, your serial interface of your laptop. That could either be through putty or Teraterm or Terminator kind of third-party solutions. Next, very common debugging protocol between devices is JTAG. JTAG is a short form for Joint Test Action Group. This protocol is being used when one component need to interact with more than one component available on the board. So, as an example, let's say microcontroller unit need to interact with flash ROM, then it need to communicate through Wi-Fi and also need to get data from the sensors of the board. So in that place, instead of UART, you might find a JTAG connection. In this case, you'll also find a clock signal pin in JTAG connection because you are sending the data from one component to more than one component through the same data line. As a standard by ARM, you might find a JTAG connector of 14 pin or 20 pin on the board of the device, but this is not always true for all of the cases because for JTAG you can customize the pin and the sequence of pins. So as a common pinout, you need five most common pins in the JTAG, that is TDI, TDO, TMS, TCK, and TRST. Additionally, there would be a ground. So as you can see in this particular figure, this is a 14 pin connector of JTAG, out of which you need to identify all the pinouts required for JTAG connection. To make this task easy, we have a separate hardware tool called JTagulator, which makes this task very easy to identify all the pinouts of JTAG. So what you need to do is you need to put all the JTAG pins into the header of JTagulator and start JTagulator operation. But by brute forcing all the pin function, it can identify and can tell you about all the required pinouts like TDI, TDO, TMS, TCK, and TRST. Then once you identify all the pinouts, you need programmers to read the data out of it. For those we have most common programmers like JLink or ST-Link, specially for ST programmers. These programmers commonly come with 20 pin header and you can choose to connect all the required pin into the programmer to the board of your J device. So here is an example when you have connected your board's JTAG to the J-Link programmer. This is how you see the data out of it. So in this particular example, you have dumped the complete firmware of the microcontroller unit by tapping into the JTAG connection of microcontroller unit. And you can see all the firmware and offsets of the MCU. connection. Once you dump the complete binary of microcontroller unit, you can save it, analyze it later, and also do a reverse engineering on this binary. To view this binary, you can also use hex editor. Also, you can use strings and other reverse engineering tool to find out the most significant data out of it. Next, very interesting and easiest to support protocol is I2C protocol. It is easiest because you need to identify here only two lines. One is SDA data line and other is clock line SCA. It is basically a asynchronous communication where you can have multi-master and multi-slave on the single line of data and clock. The clock signal is always provided by master to communicate to the peripherals by saying that whether the master is reading from or writing to the address offsets. So the advantage here is master can send the data to any peripheral it requires and only with the same two data lines. Out of which one is actually for data and other is a clock signal. But the disadvantage here is that master can talk to one slave at one time, not more than that. And to identify the communication of SPI, the best thing to use is logic analyzer because there you see the clock signal going along with the data, and when data is transmitted successfully to the slave, it is going to send a acknowledgement or not acknowledge signal to the master. Same way we have other protocol which is called SPI protocol. This is similar to a protocol which is JTAG because this is also synchronous and use clock signal and can send data to multiple peripherals or slave at one time. That means if wanted to connect to n devices, it requires n data lines to communicate with them. And since the master needs separate line for each slave, it a complex architecture of the device board. The data lines are multiplied by the number of slaves or the peripheral you wanted to connect to the master. Most common pins for SPI which is required are master out slave in, master in slave out, clock and chip select. So as a benefit of SPI is that this is faster and can support multiple slaves. But at the same time, there is an overhead of having more signal line according to the number of peripherals you are using, and it makes the board architecture very complex. To understand the SPI communication, again, logic analyzers are the best option to read the data. Apart from logic analyzers, there are programmers specially for SPI through which you can read the SPI data. So here is a comparison between SPI and I2C. As we discussed, you can see here that in SPI there is one master and three slave. Same in I2C, there is one master and three slaves are there. But in I2C, there are just two lines slave, and in SPI For each slave, you have separate data line. But in case of SPI, master can send the data to any slave at any time. But in I2C, one master can send the data to any slave, one slave at one time. So till now we have discussed few of the hardware protocols through which we get data out of the embedded device board. But once we have the data out of the device, we need to analyze that. So through the dump, we can extract the firmware, we can find out the specific required information from the binary, we can find out the hard-coded secrets like passwords, credentials, keys. We also might require to emulate the firmware to understand how the functions of embedded device are working. So let's take an example where firmware is generating a runtime key which is used for communication. So there you can emulate the firmware and find out in the functions how and where it is generating the key and on which place or offset of address it is storing. By doing that, you can exactly going to get the required information out of the binary. You can also require to do a debugging on the binary by IDA Pro. You can use binwalk to extract the file system out of that binary. So when you say file systems of those embedded devices, these are some common used file system in any of the firmware's binary. And all these file system are supported by binwalk, so you can do a extraction of those file system through binwalk itself. Apart from binwalk, you can also use FMK, that is firmware mode kit, which is again a very useful tool for reverse engineering of binary and supports most of the common file system for the firmwares. So just to give an example how binwalk works, you need to use binwalk tool with the option -e and put the correct firmware there. Once the successful extraction done, you can see the directory of your firmware's name and you can find out the present file system in the binary. And once you have the file, you can find out more significant data out of this file system. So that was a very brief introduction about the hardware breaking out of any of the IoT or embedded device. And as an outcome of all the things we have discussed in this sessions are that we need to have a secure hardware component implementations, like we have readout protection, we have obfuscation, we have encryption, we have certificate exchange to happen to secure the binaries and the data into the device. And yes, again, we have encryption at rest. At the transit, we need to maintain the integrity of the firmware so that nobody can change it. We need check for authenticity of any command or any access to the device. And also we need to consider all the business flows could be present into the device architecture. So that was it about this session. We have a lot more to talk about IoT devices and hardware reverse engineering, protocol fuzzing in hardware API side or hardware component reverse engineering side. We will look forward to talk more about this topic in future. So as of now, I wanted to thank to my team in which contributed to IoT reverse engineering and security. And I thank you to give us a chance to talk about this session on IoT hardware. You can reach out to me personally on any of the social media channel or through mail. And lastly, I wanted to thank H1 Hacks team to conduct this session and giving me this opportunity to talk about my interest into security. You can reach out to H1 Hacks page community on Facebook or in Twitter. You can find out our videos of H1 Hacks on YouTube channel also. If you have any suggestions regarding sessions, you can mail us at h1hacks@gmail.com. Thank you so much. Thanks for being a part of it. Have a good day. Bye bye.